In the last class, we have seen, right, how to design the like pipeline-based processor, right? So here, what we did, like here we split the delay component such as, right, instruction memory, right, register file, ALU, and the data memory into the 5 stages, right? And then within the stage, we have the stage register. So what are the content inside the stage register? They are nothing but registers, right? Here in this case, right, here if you see for add type instruction, here we stored entire instruction itself, right? And that is size is 32-bit, right? However, in this case, IDEX stage register, right, you can see this one holds the 32-bit, this one is also 32-bit, right? This one is 6-bit, right? And RD is also 5-bit. Got it? Here also, this ALU out is 32-bit. Got it? They are not equal, right? For this instruction add, right? So here you can see this register, I mean this stage register holds the 32-bit. Here in this case, 32 plus 32 plus 6 plus 5. Here 32 plus 5. Got it? Okay, so in the last class, we did not incorporate this register write signal, right? So we have to write the result. Okay, got it. So now in the last class also, I mean, Ankit said like here you can see we are performing the PC plus 4 here, right? Now in the multi-cycle approach, we were adding this value using the ALU, right? Now can we use ALU for this? I mean, we can use it, but what will happen then? Because if you remember this principle, right? Here we are saying that the input of a sub function is totally coming from the output of the previous sub function, right? Now that previous sub function is far away, right? Right. So this is here we want to perform PC plus 4, right? That was the question, right? Okay. Now PC will come from here. In between we have 2 stage. We have to pass the PC through this. Then you can see, right? I mean, if we perform here PC plus 4, how many cycle delay would be there to face the next instruction? 2. Got it. So because of that, we need additional circuitry. Got it? And other thing is that here you can see all these forward path, right? They are going through the stage register. It's not it. You see, these are the stage register. However, you look into the backward path, right? They are not going through the stage register. Like here, you see, this is the backward path, right? Got it. So this ALU out and RD. Why? What is the reason? Can we send them through the stage register? What will happen? These stage registers are nothing but like see, at the end we will find the clock, right? And that clock would be given to all these stage registers, right? Got it? Also PC, right? Also this register file, right? Now you see, right? So if we put this backward path inside the register, I mean stage register, then what will happen? After every clock, like here you can see this RD, right? So actually connection is like this, right? RD is there and we have the connection. So RD will appear here after the, like here, let's say if this is the ith clock, then the value what we have here, it would appear here I plus 1th clock. It's not it. Got it? So in that way, if we put this backward edge inside the stage register, what will happen? Delay will increase, right? That's not it. But we want to perform that operation quickly. So because of that, we are not inserting the backward path inside the stage register. Okay, clear? Okay, so then we saw this B type instruction, right? Okay. And then now today we will see the data path for J type instruction. If you remember J type, so opcode and then 26 bit, right, would be the address, right? So what we have to do? First, we have to fetch the instruction. So to fetch the instruction, what we have to do? We have, and the instruction address, right, that is stored in the PC. So first we have to bring that address to the memory address of this instruction memory. Got it? And then, right, so instruction would be available here. Got it? So in this way, right, we will here. So same way, we'll reserve the register or space for opcode, right? And then if you remember, we can directly allocate this. But if you remember the add instruction, right, we have already allocated this RT, RD, right? So in that way, let's say they are there, right? This RT, sorry, RS, and then RT, right? And then RD, right? And the shift amount, right? And the func field. Got it? So if we concatenate this content, right, then we'll get back this address, right? So let's say we are performing the got it. So let's say this is the concatenate operator, right? Then here we'll get the this 26-bit address. Got it? Then what we have to do? We have to align this address, right? So left shift by 2. Got it? So here we'll get 28-bit. Got it? Then what we have to do? Right? Also, right? So we need adder here. Okay. Okay. So we need PC here and then 4. Okay. So now, so from here we'll get 32-bit, right? So we have to take the first, I mean most significant 4-bit, right? So also we have to perform the concatenation, right? Okay, so let's say that bit is coming 31 to, right, 28. and then from here that 26 bit 7 bit is coming, right? I mean 0 to 27, right? Now here we will get the 32 bit. Got it? Now what we have to do? We have to give this value to PC, right? And now remember, like as this is unconditional, right? That means jump will always be performed, right? But also, like if you remember, I mean we use this PC to fetch the next instruction, right? Now PC is getting value from two different source, right? So one source is this one, right? And other source is this one. So we have to incorporate which circuitry? Multiplexer here, right? So what it? Let's say 0 and 1, right? Got it? Right? So 0 means we'll connect, right? And now if it is 1, then got it? And here it should be jump. Okay.
If we are going to make a jump, which is unconditional, the next instruction won't be implemented next.
Yes, that is there. So in the last class also you asked this question for BEQ.
Why are we adding?
So this is called hazard. We'll deal with that. Okay. Okay, we'll see. Right.
Saying that we should minus the length, which it should be sign extension, right? But raise it from 26 bits to 28 bits.
No. So if you remember, here we are getting 26 bit, right? And now our memory, like it is dealing with the instruction, and instruction length is 32 bit, right? So we have to align, because this is address means this is nothing but the offset, you can say, right? Now we have to adjust this one in such a way that it can align with the boundary of an instruction. Because of that, if you remember, we are multiplying with 4, and that multiplication is nothing but this shift by left shift by 2. In that way, if you consider this is nothing but offset, then it is telling, got it?
But in that circuitry, we use sign extension as well.
No. Here, because of that, see here we are concatenating the PC. PC is 4 bit. Whatever the PC value, sign extension, for BEQ, right? We are doing the sign extension because it is 16 bit, right? And also it is PC relative, right? Now here in this case, sign bit is coming from the PC itself. It's not it. So because of that, we are not performing any sign extension. Most significant bit, that is sign bit only. Is it okay now? So now we'll see the load one. Okay. So tell me, so what we have to do for load one? We have to first fetch the instruction. So we have to bring the PC's content in the address field of this memory. Okay. And then we'll read that value, right, that instruction. And same way, we have to store the opcode here, then RS, right, RD, then shift amount, and then func field. Got it?
Mm.
Now what we have to do after this? We have to read, right? We have to get the absolute address, right? So RS will come here. So let's say this is read address A, and then so Prothomes, we need offset. How can we do that?
RD, funky and if
So we can concatenate these three things, right? That's not it. Okay. And then what we have to do,
find extension.
right? So sign extension, then what could be the wires length? I mean, wires width would be here like 32, right? Then what we have to do? So we have to allocate the register, right? And what could be the register width here? 32, right? Let's say that is also sign extension. Okay. Now we have to read that value and we have to store here. And let's say that is the RS. What would be the width? 32, right? Okay. So now what we have to do? Tell me what we have to do,
Add it in it.
right? Got it? So why we are not aligning it here? Because this memory, right, this DM, right, so it is byte readable, right, half word readable, and also writable, read write, right? Got it? So here now we have to generate the ALU control signal. Okay. Now to generate these control signals, right, we need inputs. What are the inputs do we have for this one? Now this ALU decoder needs func field. Now you see from where we could bring this func field. So it is here, right? What do you think? Should we connect like this? Right? So we have to, let's say we have the func field, and then like there would be connection, like, you know, I mean, here if we draw every connection, then it would be complicated, right? Got it? Now at the same clock, right, will, I mean, here AC would be stored as well as func field would be stored, right? And then we'll provide it to the ALU decoder and ALU op. Who will generate this ALU op? Controller, that we will see. Okay. Now here we got this effective address, right? Now here we want to store that address. So that is ALU address or ALU output, right? What could be the width of this register? 32. Got it? Now you see, now let's say if we have only one memory, meaning that data and instruction are stored in one memory, then what we have to do? We have to bring, right? We have to write here. Now that time, what will happen? We have to also fetch the instruction, next instruction. Now two operation would happen at the same clock. read and write. Can you do that? See, that leads to the hazard, and that is called structural hazard, that we will see. Got it? So because of that, we have this extra memory, that is data memory. Okay. So here memory address, right? So we'll read that value, right? And then we'll store it here. Okay. So let's say that is TM out. Okay. Now, so data is available here, right? Now we have to write back the data into the register file. Got it? So now we have to provide the, so let's say we have the write data here, okay, and we need write register address. Now tell me the connection of this register address. Hmm? So you are saying, can we connect like this? Prathamesh? See, you have to be, no, no, why no?
But someone else might be.
Yes, right? Some other, see, here LW is waiting, right? Now see, before that, we have 3 stage. Some instruction would be here. And if we connect this RT with this, right? Let's say add is waiting here, right? So adds RT would be here. What happened? You're laughing. Tell me, I mean, what happened? Got it. So adds RT value would be here, right? Then load would write in the wrong position. So what we have to do? We have to, right, send the RD along with the data, right? I mean, got it. So let's say this is the RD. Okay, so connection would be there, right? Similar way, we have to reserve the RD here. Sorry, RT, right? Sorry, RT. Got it. Now, so data and address, they are aligned now. Now we can connect them. Okay. This is the right address. Okay. Okay. So also we have to provide register, right? And also here we have this memory, we have memory read signal. Okay. You have to activate that. Got it? Clear?
There might be chances of.
That now, yes, that we will see. Yes. Right? Tell me the situation, or you can think like.
Yeah, let's say using add and RT is being used, so that will be over.
Right? Override or overwrite or what? I mean, so that we will see when we will combine. Okay, that's why. Okay, after this we have SW, then we'll see. Okay. So, okay. Is it okay or? Okay, so another thing is that we miss the like increment of the PC value, right? So here, okay. So here, let's say we have here, okay. So 4, Okay. Now, okay, is it clear now, or now we have store what, right? So same way, right? PC is continued come here, right? Then we will fetch the instruction. So it will have opcode, all those field, right? Got it. And then we have to, so let's say this is RS, we have to read that value. So RA, got it. Also, okay, RT need, let's say that is RB. Now here we'll have RS data and then RT data, got it. And now also we need the offset, got it. So similar way, we have to concatenate, right, those field. So RD, right, and then we had shift amount, right, and then got it. So we have to concatenate here them. Okay, that connection is so there. Then we'll get the offset here. Okay, now we have to extend it. It's not it. So let's say sign extension, and then we have to store it here. Got it. And then we have to, right. So we'll get the value, the address, right, LU out, and then we have to bring the C. We want to, so here, yeah, right. So here, this is the memory address, and we have to provide the data. So where is the data? Right? Data is in this IDEX stage. So we have to bring this data from this to EXMEM stage. Got it. So let's say and then we can give it to here, and we can got it. Clear? Okay, and similar way we have to increment the, right, PC. Okay. Okay, so now we saw individual instruction data path. Now we have to combine. Okay, so let us take that example that you were saying, right? So here we want to combine LW and R type or any add, right? Let's say. So what will happen? So if you remember, right? So here, sorry, if it is R type, right? Then RD would be the destination, right? Now if it is LW, right? Then RT would be the destination, right? And both of them, right, want to write into the register file. Got it? Now if we go back and see, right, now LW is writing from the this stage, right? However, if you look into R type is writing from here. after EXMEM. However, LW, right, is writing from mem, right, write back. So one writing is happening from this place, another one is happening from this place. That means, right, here, so let's say this is our register write data, and let's say this is the address. Got it? Now both of them are getting value from, right, from this place and then this place. Clear? You clear? Because see, for add it will write from here, so it will write onto the register file and using this address and data field, right? I mean this is data field, right? Similarly, from this LW is trying to write. So both of them, let's say at the same time, add is here and LW is here. You see? So collision would happen. Then what will happen? Pratham, what to do? Both of them are trying to write at the same time.
Can you just buffer me?
So other than that, मक से कैसे होगा? Got it? So you cannot do it using mux, right? So how to resolve this issue? So in MIPS, what they have done, so they are saying that bring that content into this stage also, and then, right? So in that way, only one instruction would be there. Got it? Same way we are giving the buffer like here. So what we will do? So if you remember, for art type, right? So data would be available here, right? Let's say that is the ALU out, right? Now we'll store that one here, right? So that is, let's say, got it. Similarly for LW, right? So data would be stored here. Got it? Right?
But this will increase the number of cycles for add.
Yes.
So that like a drawback.
No. We want, what is, why have we used this one? To achieve CPI as
That's possible.
one. Per clock cycle, one instruction should be finish its execution. You see, per clock cycle, we will see only one. It's not it. Got it? So then we have to connect it like this. Got it? So here, what could be the signal name? So, okay, so let's say that is mem to reg. Okay. So mem to reg. Okay. So let's say if this is 0, then let's say we'll choose LW. If it is 1, then we'll choose. Okay. Okay. Now this is for data. Now how about the address? Right. So if we write from this place, right? we need only one address, right? And that can be either RT or RD. Then we have to choose, right? So we will bring RT, right? When we will fetch, right, instruction, then we will have the opcode RT, right? RD, not it, and also RS, right? But here we will bring RT and RD, got it? Now after decoding, we'll know, right, what is the instruction, right? Got it? So let's say 0 and 1. Okay. So we can say signal name is register destination. Okay. Got it? And then what we have to do? We have to bring that one here. Got it? Similar way, it can be either RT or RD. Got it? And then we have to connect it here. Got it? Prathamesh. Now it resolves that hazard issues, right? Oh, okay. We made mistake, right? So this is value, right? So this is data, right? So if it is data, then got it? Okay. And then what we have to do? We have to say, right? Read write. Similarly here, one time it would be mem read, right? Okay. Here. So in this way, MIPS resolve this hazard issue. Clear? Okay. So now let's say we have combined the data part, right? Now, right? I mean, these two, right? We have to also consider the other instruction, right? Then in this data path, what are the different component we have? The stages and the stage register, right? Now tell me, if we have the stage, right? And in this, in each stage, we'll add all the instruction. Then what circuitry do we need there? Right? We have to insert multiplexer. Now for stage register, we have to. So we have seen stage register content for individual instruction. Now what we want to do? Then, so if we take the union of all of them, then we are done. That's not it. Okay. So see, in some registers, let's say here, right? Let's say this is our, let's say, mem ex stage, right? So for add, it maybe needs 2 register, I mean, of size, let's say 32. Now for other instruction, let's say LW or something else, the same stage we are talking about, it needs another 5 bit, let's say. So what we will do? Hmm? We can combine, right? Easiest way. We can merge it, but you want to optimize it, let's say, then you have to select, you have to reuse this already allocated thing, right? So optimized version could be, right, would be reuse the already allocated space, right? It's not it. Okay. Now let's say, so this is the combined data path, right? Okay, right. Now here in this data path, we don't have the jump instruction, right? Now if we want to have the jump instruction in this data path, what we have to do, right? If you remember, so we have to perform the sign extension, sorry, alignment left shift by 2, and then we have to concatenate the PC's most significant 4 bit, and then that value would be available here, let's say, right? So this is, right, let's say we have this one, okay. So whatever they will choose, then they will appear here. Now if it is jump instruction, then that so then PC plus 4's most 4 significant bit, right, and then jump instructions, that bit that would be available here, and then we can connect it to there, right? Got it? So now we have this 10 number of, any doubt? So now we have this 10 number of control signals. Now how will you generate that? Let's say if we try to answer this question, let's say we have one water pipeline. Now we want to add some minerals with the water after every 1 kilometer. So what, how will you solve this problem? So, so this is the pipeline, right, flowing the water, I mean carrying the water, right? Now we want to add minerals. That for that purpose, what we have to do? Can we send it using one pipeline, or, right? So we need additional pipeline which will run parallel with the other one, right? Got it? Let's say this is the 1 kilometer. What we have to do? Join them, right? You have to create the part here, right? Got it? Got it? So this is, let's say, right? Okay, got it? Clear? Now think about like, can we borrow this idea and we can apply it in our design? What we have to do? Right? So the same stage register that we have, we can extend them. Got it? Right? Now, okay. Now you see, right? Like I mean, so we have seen two strategies, right, to generate the control signal. So this table, if you remember, this is for the single cycle one. Now this is for the multi-cycle one, right? Now which one would be used? So we have individual stage, right? If you, right? So these are the stages, right? We need some control signal here, right? Tell me, I mean, can Can we use multi-cycle? And here we are assuming that each stage will take only one clock cycle. So we can generate, right? You see, let's say we have to generate the control signals, right? So for phase stage, we have to generate, if it is jump instruction, then jump, otherwise no, right? For decode, there is nothing, right? For execute, we have this set of signals, right? For memory, we have this set of signals, right? Then we can say we have, let's say, right, T0 state, that is for fetch, let's say, T1, right? And T2, like this, T4, right? Now, during T0 state, we can generate jump. T1, nothing is there, right? So from here, we can generate like ALU SRC, right? ALU op. ALU SRC means, so ALU's hand, right? That we did not, I mean, that we have discussed for single cycle and multi-cycle, but here we didn't combine them, right? But let's say the multiplexer would be there. We have to control that. And because of that, we have ALU SRC. So we have to generate that control signal, right? From here. Got it? See, so in that way, the strategy we are seeing that, okay, so for each stage we have some controller, right? And let's say this is T0 that we have seen, right? T1, right? Got it? So this could be one strategy. Like how are we generating the control signal? If you remember, there would be decoder, right? That will check the instruction type. So in this case, so every time it will search what are the type of instruction, and then it will generate the part of the signals. The part of the signal means this, right? It's not generating full. Right? So here in this case, only 1, 3, right? Clear? So now here also we'll have if and that decoder, right? Here also if and decoder. Got it? So every time it is checking. Is there better way to generate control signals? Because you see every time, so if we have 5 stage, right? 5 condition would be checked, right? So let's say if we consider the single cycle strategy. So during single cycle strategy, right, we generate all the signals, right? And then what we can do, like, right? Got it. So here, this is the strategy 2. Here we are generating all the control signals, and we have stored them in the registers that we have seen, right? So we'll extend the stage register, that is for data, and this is the blue color, right? That is for the controller, right? Same way the pipeline that we see, right? We saw, right? Got it. So tell me, which one is better? Which, because here only one if we are checking, and there every time it is, right? This one is better, right? Okay.